fats, carbohydrates, what's the best way to burn fat, are carbs bad, what's the best way to eat, should you eat more carbs, more fat, what's the best way to exercise to burn off what you want to burn off. And this profession is full of opinions regarding what you should eat when it comes to your macros, which is your fats, carbohydrates, proteins, and alcohol if you have alcohol, and how you should exercise to get peak performance and to burn off fat. But before we go down that path, what's really important before you say anything, wouldn't it be important that you really understand what you're talking about? Because a lot of people say far more than what they know. They have a very strong opinion, and many times that opinion is based on other people's opinions, or an expert's opinion, or the collective of opinions, and you become an expert in someone else's opinion or opinions. How about we start thinking for ourselves and start to do our own research into the fundamentals of macronutrients and physiology, so we can make good decisions based on founding principles rather than sharing my opinion which is based on someone else's opinion. So let's have a look at fats and carbohydrates in this session. I'm not going to talk about proteins because proteins is more of a building block of the body rather than a good source of fuel, where your fats and your carbohydrates are your main sources of fuel for metabolism and performance. And obviously I'll park alcohol completely on the side for the benefit of this session. So let's have a look at some fundamentals of physics, chemistry and physiology. Here's some basic rules of physics. Energy cannot be created or destroyed. It can only change its form. Matter cannot be created or destroyed. It can only change its form. So I'm going to use some simple analogies. The universe, or our world, is all made up of atoms, and atoms are the smallest building block of matter. And if you combine two or more atoms, then we call that a molecule. So the world's made up of molecules, or fundamentally atoms. So I want you to imagine when I was a kid I used to play Lego. So I used to create this little city, little trucks and little houses and all sorts of stuff out of Lego pieces. So I want you to imagine that everything's made up of Lego, and each piece of the Lego is an atom, and you combine them all together to make what you want to make, whether it be a house, or whether it be a shed, or whether it be a car, or whether it be a truck. And in my Lego world, I have the ability to, I'm going to change this truck into a car. So I'll pull it apart, and I use the pieces I want to use, the atoms I want to use, to build a car. And there's going to be some leftover pieces of Lego or atoms, and that might be thrown into the universe, back into my box of Lego where I can use later, or I may want to use some of those pieces to build something else. And when it comes to fat and carbohydrate, that's pretty much a good analogy to explain, because a carbohydrate molecule is made up of those Lego pieces, and a fat molecule is made up of Lego pieces as well, but they're made up in a different way. The truck and the car is all made up of Lego pieces, but they're made up in a different structure or a different format, and some may have more pieces and some less pieces, and there's going to be some leftover pieces which I can use for something else. So what are those pieces, and how do I put them together, and how do I break them apart, and how do I put them back together again, and what do I do with the leftovers? And that's a good way of looking at when it comes to our universe. Now, all energy on our planet originates in solar energy, which is the sun. So without the sun, we have no energy. So the sun produces, with this big ball of fire up there in the sky, energy. And that solar energy comes down to the planet, and a organism that's really great at using that energy, because it doesn't have the ability really to produce its own energy, are plants. So plants will take that solar energy and use that solar energy to build its building blocks, or his little Lego pieces in the plant. And it will use that energy and it will form plant matter, which is through the process of what we call photosynthesis. Now, where does plants get its matter from? Well, floating in the Lego box, or in our world, the Lego box represents the atmosphere, we have pieces of Lego which we can't see because they're so small, such as atoms and molecules that we can't see. So in the world we have floating around carbon dioxide. Carbon dioxide. So carbon dioxide is made up of carbon and oxygen, carbon dioxide. Now, so the plants in the world have this amazing ability to draw from the atmosphere carbon dioxide, and it will also combine that with water, H2O, because if you don't feed a plant it dies, right? So we give it water, H2O, we hydrate the plant, and it will combine carbon dioxide with water, H2O, and it will form carbohydrate, means it hydrates the carbon. So carbon dioxide, CO2, and your water, H2O, and the plant will produce carbs, what we talk about, carbohydrates, in the plant, in the forms of fruits, vegetables, grains, and cereals. And depending on the molecular structure, it will be called different things. It will be glucose or fructose, obviously through milk products we have lactose and galactose, and we have different types. So for this session I'm not going to go into the different types, but fundamentally all the types have a backbone, a skeletal structure of carbon. So it's a whole chain of carbons combined to form different types of carbohydrate, which we also call in a refined form sugar, sucrose, lactose, fructose, and glucose. So there's different types of ones, whether it be saccharides or disaccharides. I'm not going to open up that Pandora's box, because that's not the point. But all of them are based on the molecular structure of carbon combined with different molecules and atoms. So then what we do as humans is that we eat the plants, we eat the fruit, the grains, the cereals and the vegetables, and we take it in and then we store that, or we use that in the form of carbohydrate, which is in the food form. When I eat it and gets broken down into the blood, it's called glucose, and when I store it into the cells of the body, whether it be the muscles or the liver, it's called glycogen. What's also very interesting is if you look at the other macronutrient, which is fat. Now, it's easy to think of carbohydrate because in the word carbohydrate it's carbon and oxygen, hydrated carbon. But fat doesn't give you a clue what it's made up of. But if you look at fat from a molecular structure of the Lego pieces that it's made up of, it's made up of the same pieces that carbohydrate's made up of, but in a different structure. My truck is made up of the same pieces as my car, but it's made up in a different structure, in a different order, but it has the same pieces. So fat is also, all fats, doesn't matter what type of fat, whether it be a polyunsaturated fat, a saturated fat, or monounsaturated fat, all fats are made up of a backbone or a foundation chain of carbon atoms, and attached to those carbon atoms are hydrogen atoms. So if every carbon atom has two hydrogen atoms connected to it and have a chain where they're all joined together and they're saturated with hydrogen, we call that a saturated fat. If there's one break with a double bond between the carbon atoms, there's only one, that's a monounsaturated, and if there's more than one, we call it polyunsaturated. So again, I'm not going to go into that, but that's where the names of the different types of fats. So basically they're all still made up of the same backbone of carbon atoms, and they have attached to them hydrogen atoms and oxygen. So fats are carbohydrates basically made up of a backbone of carbon atoms with a combination of hydrogen and oxygen atoms attached to it. So a lot of people think fat is completely different, but it's not. And that's why if you have too much carbohydrate that you can't store it, the body has the ability to take that maybe car, Lego piece, the little carbohydrate car, and all the garages on my Lego land are full, and I need to store it in the truck yard. So what I do to get in the truck yard, it has to be a truck, so what I do is I break apart my little car, carbohydrate car, break it all apart, and the body will rebuild it into a fat truck, and then that will be able to store it into the truck yard, which is the fat cell. So trying to make it really simple to understand without going too much into biochemistry where we all get confused. But basically I can restructure carbohydrate into fat in that process of the breakdown. And that process only happens once all the cells, the storage cells in my body for carbohydrate or glycogen, are full. And if they're not full, that process won't occur. You won't convert carbohydrate into fat if I still have parking spaces, car parking spaces, for my carbohydrate cars. It's only when all those are full that the body needs to decongest the roads of my Legoland, which is the blood vessels, the vascular system, so it doesn't destroy the roads or the blood vessels through deterioration and clog them up, such as atherosclerosis. And if you have lots of carbohydrate cars, that causes lots of damage. So what I do then is that my body will say, how can I decongest the blood vessels, the highway or the streets that transport everything through my body? You need to store them away, and I'll break them apart and store them into the truck fat yards, but I have to convert it first into a truck. And that process is technically called de novo lipogenesis. So you can imagine that it's easy to store carbohydrate, and if I eat fat, it's easy to store fat because they're already in the structure, the storage structure and the usable structure that they are. But if I need to convert one to the other, that's a more complex process, and the body will be able to do that, but it will be a last resort. So how do I basically get rid of my carbohydrate molecules and my fat molecules in my body? Well, the body needs energy for metabolism, for mechanical energy such as movement and exercise and performance, electrical energy for nerve transmissions and thinking and so on. So I need that energy. So remember, energy cannot be created or destroyed. So where do I get the energy? I consume the carbohydrate, and I also consume fat, because fat is also present in things such as grains and cereals and vegetables. So I'll eat fat that way. Or there might be a intervening process where the animals or the cow eats the grain or eats the cereals or eats the vegetables, whatever it might be, and then I eat the cow. And when I eat the cow, I get obviously protein, and I also get fat from the cow or the animal. So that's a two-step process. So I get fat directly from the plant, I get fat from the plant that goes to the cow, and I eat the cow, and then I get fat, which is again the same molecular structure when it comes to the components that make it up as a carbohydrate, but in a different structural process, or a different structural augmentation, you could say. So whether I get it from vegetables, or whether I get it from fruits, or whether I get it from cows, it all comes in as carbohydrate and fat. It gets into the blood as a form of glucose or free fatty acids. It gets broken into free fatty acids, and it's stored in the body, in the cells of the body, either as glycogen or triglycerides into the fat stores of the body. So where do we go from here? Now, how do I use that energy? Now, a couple of things about energy. Energy is stored in the bonds of the molecules. So if I put two molecules together, it takes energy to form a bond, but if I break a bond, if I break two pieces of Lego, energy is released. So the body has to access the energy that's in the molecular bonds of the molecule. And how to do that? It attempts to break a piece of Lego away, or break a carbon atom away, and that itself will release energy. And that process of breakdown is metabolism, or we call how we're burning off fat. Well, what we're basically doing is breaking it apart. But what we do is we break a carbon atom or a carbon molecule off the backbone, because that's where the energy is stored. So if I need to get energy, whether it be from a carbon molecule or a fat molecule, in that long backbone of carbon atoms, the body will break a carbon atom away, and that energy is then released. And that energy is used in the body to rebuild another molecule in the cells of the body called ATP, adenosine triphosphate, which is the rich energy cells, like petrol to a car, rebuilds that so the body can break that apart to produce energy to drive the body mechanically or electrically or even hormonally. So it's just a three-step process. You take it in, you store it, and then you need to break it apart. Same with you have a car in petrol. The body will combust the petrol by igniting it with a spark plug, and that will ignite the molecules of the petrol, breaks the bonds, releases energy, and that creates mechanical energy for the wheels to turn. And you also get a byproduct of heat. Hence, the car engine heats up when you drive it. The body's the same thing. I need to get that energy to rebuild my ATP stores, which is the main energy source stored in the cells of the body that I use for function. And when I break those molecules apart, energy is released, and I need to rebuild the ATP. How do I rebuild the ATP? Well, I break down my fats and my carbohydrate to create energy to rebuild the ATP, to break it again to drive the body. So this breakdown of carbohydrate and fat, that occurs in what we call the mitochondria for oxygen, or anaerobically. And it's a process called the Krebs cycle, which is a very complex biochemical process and formula to go through. But essentially what it basically does is breaks that carbon molecule away from the rest. So when you break a carbon atom away from the main chain of carbon molecules, then that releases energy that's used for metabolism and performance and all the great things that we do to live. But now what you've got is a shorter chain of carbon atoms, and you have a free-floating carbon atoms. And the body doesn't like free-floating carbon atoms, they're like freeloaders. You know, it's like that, you know, Craig the carbon in the nightclub who's single and he's roaming around the nightclub being a nuisance of himself. And so basically what, you know, the owner says, look, I don't want these, you know, free roaming Craig the carbon's, you know, creating a nuisance of themselves. I need to get him out of the nightclub because it's getting a bit too congested here. So I'm going to get Ollie the oxygen to come in. He's the bouncer. Ollie's the oxygen bouncer to come in into the nightclub, grab Craig the carbon and kick him out and say, off you go, you're now being kicked out of the nightclub. Well, the body does that as well. So what we basically do is that I need to get rid of that free-floating carbon molecule or atom. So therefore I breathe in oxygen, and that oxygen goes into the respiratory system, the lungs and all the alveoli in the lungs, down the trachea to the lungs, the alveoli, gets absorbed into the cardiovascular system, the blood and the vessels, gets transported down to the cells of the body via the arteries, arterioles and the capillaries, goes down and it finds those little free-floating carbon atoms and it grabs them, bonds with them and say, come with me, drags it back in from the cells back into the vessels of the body and back to the exit of the nightclub via your veins, your smaller veins and your capillaries. And then when it gets to the front door, I breathe Craig the carbon and the oxygen out. Off you go. So basically you have the breakdown of energy, whether it be from a fat molecule or a carbohydrate molecule, where I break it down, I break off the carbon, release the energy, has a free floating carbon, I breathe in oxygen, oxygen comes down, grabs the carbon and escorts the carbon, create the carbon out of the nightclub via Ollie, the oxygen bouncer, and I breathe it out. So what happens to fat and what happens to carbohydrate when you burn it off or metabolize it? Well, basically that's what you're doing. You're breaking it apart in the cells of the body and you're breathing it out. So when you work aerobically, there are two metabolic byproducts: carbon dioxide, C2O, and water, H2O. Because when I break it apart, as I shared beforehand, the carbon backbone is saturated, is connected with hydrogen and oxygen. So I have to get rid of the hydrogen, and I get rid of that through the H2O, being water. And I'll sweat that out or urinate that out of the body. And the carbon will be escorted with the oxygen molecule in the form of carbohydrate, carbon dioxide, to breathe out. So what happens to the fat and the carbohydrate that I have in my body when I burn it off? I basically breathe it out. So the more I breathe, forcefully breathe through metabolic processes, the more fat and carbohydrate I'm burning off. So I'm not including going hyperventilating, because all I'm basically doing there is I'm bringing Ollie in and out of the front door and out, but he doesn't go down into the nightclub to get Craig the carbon atom. Basically what I'm doing is going in and out of the front door, but not actually moving anyone out of the nightclub or the body. So hyperventilation is, because all you're doing is you're breathing in and out the same air rather than using the byproducts, the carbon byproducts from metabolism in the body. So essentially, if you want to burn fat, burn carbohydrate, you have to do things that force you to breathe, and the more you breathe, the more you burn. So a lot of people think it's quite complicated, but it's not. So essentially, if you want to bring it right down to the law of physics, the more you breathe through metabolism, the more you burn fat and carbohydrate. So whether you do high intensity interval training, or you do long walks where you're breathing at a slightly higher rate but for a longer period of time, or a shorter rate at a higher high intensity, it doesn't matter from a chemical point of view, from a biochemistry point of view, or even a physics point of view. However, notwithstanding, sometimes you have to take in the physiological change that training has on you. So if you, for example, train with high intensity, then it's going to force your body to physiologically change, to become more efficient at using its energy, and the body will try to do that by sparing its carbohydrate and burning more fat. But in the sense of basically energy in, energy out, that's basically the law of physics. Energy cannot be created or stored, it can only change its form. So when it comes to fat loss, it basically means energy in, energy out, and how you get that out is basically breathing in a real simple, simplistic way. But you can increase your breathing rate, increase the amount of breaths you take in a day through exercise, movement, and just being as active as you possibly can. So that's a simple process without going into how exercise and strength training would change your physiology. That's just looking at energy, the transformation of energy and the changes of energy from the plant to the body back to the universe. See you in the next Kmax.